Greetings, calculus fans. A video covering vector calculus. In this section, we'll talk about vector-valued functions. So, cover quite a bit of information here, but the good news is that most of it is stuff that you've done before, just written in a different context. So, we'll think of this vector-valued function R as a map. It takes T as an input and spits out to you a vector in R3. And with this, we'll do all sorts of things. We'll talk about graphs and characteristics of those graphs, and even do calculus on this thing. So let's get right into it. Here is the first section. We say that the vector-valued function R has a limit as t goes to a if all the functions have limits as t goes to a. So the idea here is that we'll take limits of f, g, and h individually. If all three of those things have limits, then we say that the vector value function R has a limit too. You're welcome to use all of your Calc 1, 2 knowledge to take limits of those functions f, g, and h. So here's an example. Let's go ahead and find the limit as t goes to 2 of this vector valued function R of t. So again, we'll do that by just taking the limit as t goes to 2 of those individual scalar valued functions that make up the vector valued function. So I'll write out with some painstaking detail this time. The limit of the vector valued function is the vector valued function of the limits. And you can see that in this case, we come up with a number 8, 1, natural log of 2. So that's a perfectly good vector in R3, and that's the limit of this vector valued function. Of course, just like in Calc 1, we know that limits may be infinite or not exist, and similarly here, that makes it so that the limit of the vector valued function doesn't exist. Okay, having defined limits, we can go ahead and define continuity. The definition of continuity is exactly the same. We say that a function is continuous at a if the limit as t goes to a of r of t is equal to r of a. Okay, and again, this is exactly the same definition from Calculus 1. Having defined limits, we can talk about curves in space. So the curve r of t is so we can think of it as a space curve with parameter t. So as t ranges, we're given different values of our vector valued function, and that defines for us a curve in space. So here's an example. Let's go ahead and identify this space curve. R of t is 1 plus t, 3 minus 2t, and 4 plus 4 minus 3t. So writing the scalar components of the vector valued function, we can see that this is a line through the point 1, 3, 4, and that the direction of the line is 1, negative 2, negative 3. Let's go ahead and have a look at another example. Let's identify this space curve. R of t is cosine t, sine t, and t. In this case, it helps to think about the sketch, and you can imagine that the x and y coordinates just go around a unit circle, and the z component grows in time. So here's a reasonably correct sketch of that action. As t goes from 0 and increases, we can see that when t is at 0, we start at 1, 0, 0. X and y go around the unit circle, and z just increases, again giving us this helix. Okay, let's go ahead and talk about calculus on these vector valued functions. As you might expect, the derivative is defined as the limit of the difference of vector valued functions r of t plus h minus r of t divided by h, provided that limit exists. So with that said, we can just use our understanding of Calc 1 to find derivatives of these vector valued functions. The vector r prime of t is called the tangent vector to the space curve r of t. And of course, if you want to come up with a line tangent to that space curve, the line has direction given by the tangent vector and a point given by the vector at A. Of course, we've seen that a line in three spaces defined by a point and a direction. So that direction r prime of t plays the role of v in our equation of the line, and the point r of a plays the role of r naught. So here's an example. Sorry, first the unit tangent, of course. Given the tangent vector, we can come up with a unit vector in the same direction, just dividing by the magnitude. So the vector capital T of t is called the unit tangent to the space curve r of t. Okay, so here's an example. Let's find parametric equations for line tangent to this helix, as it turns out, at the point 0, 2, and pi over 2. So in this example, we can see that the space curve is defined by the vector valued function 2 cosine of t, 2 sine of t, and t. And here is the tangent vector to that curve. R prime of t is negative 2 sine of t, 2 cosine of t, and 1, which of course is just the derivative. So we'll take v to be the direction of this line to be the tangent vector at pi over 2, and we'll take the point to be the value of the vector valued function at pi over 2. So here are those, the point r naught and the direction v, and given those, we can write the equation of the line. And again, parametric equations means writing out each component individually. So x equals negative 2t, y equals 2, and z equals pi over 2 plus t. Okay, let's go ahead and find the tangent vector and then find the unit tangent, typo there, at t equals 1. Okay, so again, the tangent vector is just given by r prime. The unit tangent, of course, is given by r prime divided by its magnitude. So here's r prime of t divided by its magnitude. And to identify the value of the unit tangent at t equals 1, we'll just plug in 1. So there's a unit vector representing the tangent, the unit tangent at t equals 1. Okay, other properties follow as you might expect. Here's a list of those properties. The derivative of the sum is the sum of the derivatives. The derivative of a scalar times a vector valued function is a scalar times the derivative of the vector valued function. We have a couple different product rules here depending on whether you have a product of a scalar with a vector or the dot product or cross product of two vectors. And finally, the chain rule, the derivative of a composition of a vector valued function with a scalar valued function, the derivative of the outside evaluated at the inside times the derivative of the inside function. One interesting characteristic is that if a space curve has constant length in magnitude, then the vector representing the space curve and the vector representing the tangent are perpendicular. And we can use properties of the dot product and the product rule for dot products to find this relationship. So if the magnitude of a space curve is a constant, then the magnitude squared is just a different constant. And of course, the magnitude of a vector squared is the dot product of the vector itself with itself. So we can use the fact that the dot product of a vector with itself is the magnitude of the vector squared to come up with this relationship that the dot product of the vector with itself is equal to this constant c squared. Now, of course, just take a derivative of this using the product rule, and we can come up with an expression that involves the vector valued function r and its derivative r prime. So here's that relationship, the derivative of the first dot product with the second plus the first dot product with the derivative of the second is 0, which we can see simplifies into 2 r prime dotted with r is 0, or r prime dotted with r equals 0. Of course, when the dot product of two vectors is 0, we know that those vectors orthogonal or perpendicular, and that's what we want to show in this case. This will come up a little bit later. This is a pretty cool property when you have a space curve with constant magnitude. Okay, it turns out that integrals are also defined component-wise, so the integral of the vector valued function is the vector valued function of the integral, and we'll just do a really brief example to illustrate that. We've got the integral of this vector valued function 1 over t plus 1 in the x direction, 1 over t squared plus 1 in the y direction, and t over t squared plus 1 in the z direction. So of course, these integrals are all Calc 2 integrals involving logarithms and inverse tangents, which we can quickly evaluate. So here we see the value of those three individual integrals. That gives us the value of the integral of the vector valued function. So that integral is log of 2, pi over 4, 1/2 log of 2. Okay, hope you've enjoyed this video on vector valued functions and a little bit of calculus on vector valued functions. Have a great day, and we'll see you next time. Bye-bye.